Hello everyone, welcome to another video of GPU programming with Mojo. Today we shall learn about GPU shared memory, its benefits and use cases. In one of the earlier videos, we have looked into the four types of memory available in a GPU. Private memory, visible only to the thread. Shared memory, visible to all the threads in a block. Global memory, visible to all the threads in all the blocks. It's also the memory visible to the CPU or the host. And last but not the least, the constant or read-only memory. The shared memory is also the one closest to a thread or a group of threads in a block. The scope is also limited to only the threads within a block. Because of this proximity and scope, the read and write operations on a shared memory is much faster compared to what you would have done on a global memory. So finding an efficient or an effective balance between the operations on a global memory and shared memory will enable us to write an efficient GPU kernel. The shared memory also has an interesting fact in the sense it does not come with data preloaded, which means we have to copy the data from global to shared memory before even trying to execute an operation. So one of the criteria or the question we have to ask ourselves is, does this prerequisite, which is the copy operation plus the execution in shared or local memory, greater or lesser than the execution on global memory? So for example, a real world scenario would look something like this. So let's say that you're trying to add 4 consecutive elements and compute a sum. Without the shared memory, you would just simply do a of I plus 1, I plus 2, I plus 3 and compute the sum, which means you would have done 4 global reads. But if you were to use a shared memory, then you would first copy to the a of global of I onto a shared memory and then perform the operation. But you still have to evaluate whether that one global read that you did plus the 4 fast shared memory reads is faster than the 4 global reads that you did. So one global read plus 4 fast reads, does it outweigh the benefits provided by the shared memory access or not, is the question that you have to ask, evaluate, and then implement the kernel. So keeping these concepts in mind, let's look at our code and implementation. The memory representation looks something like this. We have 8 elements. We have 4 threads divided into 2 blocks, and each of them will have a shared memory to perform the operation. So we'll start off our implementation with importing certain standard libraries and some initializations. Here we initialize 8 data elements. We have 2 blocks and we have 4 threads in each of those 2 blocks. So 8 threads managing 8 data elements. We'll start writing our kernel. The very first line in our kernel would be to create the shared memory or shared space. We make use of a really nice abstraction in Mojo called layout tensor, which provides us very safe and convenient APIs to handle all the memory allocations and management. In this case, we can provide the data type, the layout style, which is row major, and creation of a shared space or shared memory. After we do that, we derive the global index of the thread. We derive the local index of the thread. We add a boundary condition, which is a best practice. And then finally we perform a copy operation, which literally means a of global of I copied over to shared of local of I. Now keep in mind, shared of local of I means, in this for example, it means different things to different threads because they all belong to different blocks. So what I mean by that is, for block 0 thread 2, shared of 2 means it's fetching the element from A of 2. Why? The global index for this block 0 thread 2 is 2. The global index for block 1 thread 2 is 6. So in the second scenario, A of 6 is fetched and stored in shared of 2. In the first instance, A of 2 is fetched and stored in shared of 2. So visually representing it would look something like this. So this thread will get sixth element and store it in shared of 2. This thread, again called by the name T2, will fetch A of 2 and store it in shared of 2. So the commonalities between these two is both are called T2, both are storing it in shared of 2. But note that they belong to two different blocks and hence they mean two different mutually exclusive locations. Their global index uniquely identifies them and hence they are able to fetch the corresponding element from the global memory or the global array. So this is essentially copying the corresponding element from the global memory onto its corresponding shared location or shared memory. After we perform such an operation, it's a best practice to call what's called as a barrier function. This ensures all the operations performed prior to this are visible to the ones after it. So essentially think of it as a synchronized function. It ensures that the operations you did, which is to copy before, has gone very safely and correctly. So when you perform your operation after this line, everything is in order. So it ensures thread safety. The order of operations has been performed in a correct and accurate manner and handle all the nuances between them. So this is like a safety check or a synchronization check before you perform your actual operation. So this is a best practice used whenever such shared memory is involved. Once we call that, we again use the boundary condition as a best practice, after which we perform our operation, which is nothing but add 10 to all the data elements to the array or the vector. This diagram is shown just to elucidate the fact that every thread gets a copy of this kernel. So hence, when they execute the kernel, the index, the local index and the global index for each one of them is different. Now, coming to the final part of our implementation, we get a context to the GPU, which is a reference or a pointer to the GPU. We create a buffer to store our output. We create a buffer to store our input and fill them at 1. And we call our Q function, which calls the GPU kernel and executes them with all our parameters. Finally, we call the synchronization just to ensure all the operations has been performed safely and accurately. And then finally, we print out our result. So we initialized all of them at 1 and we're adding 10 to each one of them. So the result is expected as to be 11 to be added, and that's what we see on the screen. So this is a very simple operation for such a shared memory to come into play, but it is the point of the tutorial is to illustrate the fact that there is a concept of shared memory and should be used effectively, and so that you can perform certain operations very quickly instead of relying solely on the global memory and putting a stress on it, as well as also reducing the efficiency of your read and write operations. So use shared memory whenever there is a lot of data reuse. And another clue where you can use shared memory is when you are tapping into the neighboring elements. For example, in the concept of pooling or convolution, you depend on your neighboring elements and perform an average or a sum operation. When such patterns come into play, almost always you have to make use of shared memory because it's a primary candidate to use in those scenarios. So the key takeaways are shared memory usually is 10 to 30x faster than global memory for read and write operations, but it involves an additional step of copying the data. Use the barrier function because it ensures that all the activities prior to that are done safely and correctly. And whenever there is a neighboring element access or data reuse, shared memory is a very essential part of it and a primary candidate to use in those scenarios. Hope you understood shared memory and all its fundamentals. See you in the next video. Thank you.